Hello, my name is Yunfei Hao. I'm from the California State University, San Bernardino. I'm going to tell you about our project on building a smart parking system on our campus. So on our campus, we have over 7,000 parking spaces, and there wasn't any parking monitoring system before our project. So we started with setting up a pilot project in one of our parking structures. Our objective is to provide real-time information on the number of available parking spaces in that parking structure. Well, we also set a few goals for these projects. Firstly, we want to achieve a high accuracy in terms of counting the vehicles. We're going to utilize both computer vision and IoT sensors. Our second goal is to set up the system reliably, but also with lower costs. Our budget for the equipment is about $15,000. And finally, we want to involve students to work on this project. Specifically, this is actually a capstone project for our engineering students. Our idea was to engage our students in research and have a project to solve practical problems. Well, we picked one of the parking structures as our pilot site. In this parking structure, we have over 700 parking spaces. That is about 10% of the total available parking spots on campus. It has 3 levels, the parking structure, and also has 2 entrances. The reason for us to choose this location, in part, is because it has a relatively simple layout, and it's a covered parking structure, so it's also easier for us to set up our sensors. Another reason for choosing this site is because in this parking structure, we already have 13 civilian cameras covering various locations in the parking structure. So this makes it easy for us to extract video feeds to validate the study, as well as implement our own computer vision algorithms. Well, there are 3 parts of our system. The first component are the IoT-based vehicle counters. Those are the wireless battery-powered sensors that we bury them under the pavement. The second component of the system are the computer vision-based vehicle counter. For this part, we're utilizing the existing surveillance cameras that are pointing to the entrances of the parking structure. In addition to that, to get floor-level capacity estimation, we also utilized some of the cameras that are looking down the ramps that's going on to the second and third level of the parking structure. And the last component, well, just as all the smart systems these days, we build a web application to provide real-time information. So let's take a look at the website we have. Well, let's start with looking at the websites that we built for this project. Well, unfortunately, the campus is closed today, so there's 0 vehicles in the system. But just to give you an idea on what's happening here, we're going to show the available parking spaces, percentage of the occupancies, and also here's a timestamp on what was the last time some vehicle triggered our sensor. Let's look at some normal days before this coronavirus outbreak. So here is a typical day of the histogram, if you will, for how many vehicles are parked in the parking structure during the time of the day. Well, in addition to just show the information from the web application, we build an API that others can extract this information and show the data on their own applications. So we have a kind of detailed documentation on what are various values that you can check and how to extract this information from the web API. Well, to take a closer look on the system, here is the floor plan for one of the entrances we have in the parking structure. We notice our sensors are buried under the pavement in this entrance to the parking structure, and our civilian camera are those pointing directly to the gates. Well, in this video, I'm going to show you what's happening with our system. So notice we're looking at the camera from here. When vehicles coming in the parking structures, the sensor will be triggered. And we notice the color in the sensor have been changed, and at the same time, our computer vision algorithms extract the vehicle from the background and tracking its movement direction. Right, so in this slide, I'd like to show you the parts that we use cameras to estimate floor level capacity. So the idea was we're trying to estimate how many cars are there on each and every floor without adding additional sensors under the pavement. So here we trained a neural network using TensorFlow and providing a percentage estimation on how many cars are currently at each level. So this is the camera at the second floor ramp, and now you see that we're doing an estimation on the capacity at this level. Well, there are quite a few challenges when building the system. Firstly, the technical challenge would be we have miscount due to the limitations of the sensors and the cameras themselves. For the sensor part, we built our own filtering algorithm to eliminate the miscount and the double count from the raw sensor inputs. So our sensors are essentially magnetic sensors. They will give you a reading once they detect the change of the magnetic field. We also built our own vehicle tracking algorithm. The reason for that is our cameras are not directly pointed to the gate. So many of the cameras are actually looking at the gate from an angle, and that causes some complexities when directly apply some of the vehicle tracking algorithms. So to illustrate some of the challenges, in here, one of the inherited limitations for our under pavement sensor is that it's very hard for the sensor to tell the difference between two vehicles moving inside the parking structure closely, as we're showing here in this tailgating scenario, versus one vehicle that is slowly moving into the parking structure. So from the sensor's perspective, the change of the magnetic field will look very similar. In this slide, I'd like to show you some of the challenges we're facing from the computer vision algorithm. So in this video, you'll notice that we're looking at the entrance from an angle. And at the same time, a large portion of the camera wheel is actually being blocked by this large SUV. On top of that, because of the moving behavior or the driving behavior in this parking lot, oftentimes people tend to be reckless when driving in the parking structures. That will confuse our computer vision algorithm. Well, here's the floor plan for the camera view that we'll just look at. So this is the other entrance of the parking structure. Our sensors are buried under the pavement, and here is the location of the camera that we just looked through. We conducted an evaluation towards the end of the project. Here we compared 3 different counts to compare the ground truth versus the algorithms that we developed. In the x-axis in this figure is the time of the day. The y-axis is the accumulated number of vehicles in the parking structure. We compare 3 methods here: manual count, IoT sensor count, and the computer vision count. You will notice that we have very good alignment for most of the day, which shows that our system is performing well in terms of counting the vehicles. There are some challenges during the rush hour here. So if you notice, the lines in green here doesn't line up with the lines in red, which is the computer vision counter here. We suspect that this is because during the rush hour, at the noontime in the parking structure, there are many vehicles circling inside the parking structure. And because of this circling behavior, it tends to confuse, or we have some challenges on handling those situations in our computer vision algorithm. And we notice this miscount has been carried out in the rest of the day. The major problem was caused during the rush hour. Well, to talk about some future directions that we're going to work on, one thing we can do is to provide not only the real-time counting information, but also do the parking prediction. Well, here I'm showing a comparison on 2 Tuesday mornings. In the first figure here, this is one Tuesday morning, and if you compare the trend or the curvature on this histogram versus the count from the week before, you will notice that the trends are very similar. And if we are going to do projections on what will be the capacity in the parking lot in this Tuesday morning, we can easily do this by looking at the history from last week. We're also working on extending this project to cover the whole campus. But due to the interruption caused by coronavirus, our campus is currently closed. So, it's hard to estimate whether or not we can deliver the system by this fall. Well, finally, I'd like to acknowledge the support from various departments on our campus. While this project cannot happen without their help and encouragement. Finally, if you're interested in what type of sensors we're using, I have these slides to show you a little bit more information on the specifics of the vehicle detector. Well, that's all I have. Thank you.